All right, questions 11 through 15. It says base your answers on information below and your knowledge of Earth space science. Some questions may require the use of the reference table. So we're moving on to a new cluster. They're introducing the carbon cycle. So they gave us some background information. It says the global carbon cycle refers to the movement of the element carbon through different storage places or reservoirs on Earth. Carbon moves through these reservoirs at different rates. Most carbon near Earth's surface cycles fairly quickly. Carbon in the atmosphere recycles in about 3 to 5 years, while plants recycle carbon in about 50. Okay, so they're giving us some different times. So the atmosphere, 3 to 5 years, plants, 50 years, and carbon found in soil and fossil reservoirs is recycled in about 3,000 to 5,000 years. Okay, so different temporal scales in terms of how we are recycling that carbon. The carbon cycle has two parts. The fast cycle involves the biological processes of photosynthesis and decomposition. The slow cycle involves the time it takes for soil, inorganic carbon, to form from the weathering of rocks and soil. Wildfire events contribute to the carbon cycle. In 2020, mega fires released an estimated 107 million metric tons of carbon dioxide into the atmosphere, equivalent to the amount released by about 23 million cars. Okay, so we're talking about wildfires here. And they're telling us that it releases a lot, like quite a bit of carbon dioxide, right? So equivalent to 23 million cars. The model below shows some information about Earth systems and the carbon cycle. So they've given us a picture. We have combustion down here, human-induced CO2 release, and they're using carbon from fossil fuels. Remember, we talked about how the problem with carbon in fossil fuels is the temporal scales are completely different. So carbon stored in fossil fuels are carbon sink. We're taking carbon out of the atmosphere. We're making fossil fuels with it, which takes millions of years, but we burn them in just a few seconds. So the temporal scales in terms of carbon sink of fossil fuels and the carbon source of fossil fuels through combustion, very different. We have our biomass carbon. So you have fossil or forests, and forests can be both a source and a sink in the topic they're talking about. So as a source, when we burn trees and plants, we are producing CO2. But when trees undergo photosynthesis, where they are making food and energy, they take in carbon dioxide, so they can also be a sink. And then we have another picture on the next page. So it says the model below represents how carbon levels change depending on what is happening with the trees in the forest. So we have forest carbon, carbon uptake and storage. So when trees are growing, they're storing carbon. Carbon release in a fire. They also release carbon when they decompose. And then we have growth again. So the same process on each side in terms of that, that picture. Okay. So it says explain the process that the trees in a forest use to make energy. Okay. Process that trees in a forest use to make energy for food, and describe. So we have that and, right? And is important. It means we have to do two things. Describe how this process is responsible for a decrease in atmospheric carbon dioxide levels. Okay. So in this case, they are talking about the way that trees are producing food. So that process is called photosynthesis. If you did not remember that it was called photosynthesis, that's okay. You didn't need that in this question. It doesn't ask you to identify the process, it asks you to explain it. Okay, so you could have said photosynthesis, but you also could have just explained what was happening. So we know that to make energy, trees consume carbon dioxide. They take carbon dioxide in, and when they take that carbon dioxide in, they are going to use it, which reduces the amount in the atmosphere. So we could say something like, when trees produce energy, they take in carbon dioxide, which reduces the amount in the atmosphere. Okay. So essentially, we are just removing it from our atmosphere through that process. Okay. So photosynthesis, we take in carbon dioxide, we produce oxygen. So it's removing some of that that would have been available in the atmosphere. All right, question number 12 says the model below shows the movement of carbon arrows through the four Earth spheres. The numbers indicate the amount of carbon naturally added or removed from the spheres in gigatons per year. The numbers in bold indicate the amount of carbon added or removed by human activity. Numbers in parentheses are amounts of stored carbon. Okay, so they're giving us a model of how much carbon is added, removed, and kind of cycling through the different spheres of the Earth with these values here in gigatons and our different processes labeled. So number 12 says which statement correctly identifies the quantitative cycling. So quantitative means we have a quantity or a number of carbon between two of Earth's spheres as a result of natural processes and human activities. So the first one, so essentially we have to check in our model if each of these statements is supported. So they're kind of like claims, and we have to see, does that claim supported by the data or evidence that they showed us. So one says fossil carbon releases 2,300 gigatons. Okay, so fossil carbon. So I'm going to find fossil carbon, and it says 10,000. Okay, that does not match that number, so that is not correct. So one we can get rid of. Two says the deep ocean stores 36,000 more gigatons than is released by air-sea gas exchange. So the air-sea gas exchange right here has a value of 90, and the deep ocean is 37,000. So if I was going to be producing 36,000 more, my deep ocean is 37,000 minus 36,000. I would have to produce 1,000 gigatons in the air sea gas exchange, and we only produce 90. So that is not true. 3, human emissions add 9 times more carbon to the atmosphere than plant respiration. So I'm going to find human emissions. Human emissions is 9, and plant respiration is 60. So 9 is not 9 times more than 60, right? So that is not going to be accurate, because actually plant respiration is producing a lot more. And that says the amount of carbon that leaves the atmosphere and is absorbed by the ocean is 92 gigatons. So let's see, that leaves the atmosphere and is absorbed by the ocean. So here's the atmosphere, and here's going into the ocean. So right here, leaving the atmosphere into the ocean is 90 plus 2. So that's a total of 92. That is true here. So that is correct. I'm going to check that off, which is the same amount that is released by the oceans back into the atmosphere and absorbed by ocean sediment. So I have to look at both of these. So released by the oceans back into the atmosphere. So here's it releasing into the atmosphere, 90. And then absorbed by ocean sediment here is 2. And so those would add up to 92, which is equal to this. That is correct. So 4 is our correct answer. Okay, and then 13, which explanation describes how climate change from increased atmospheric carbon dioxide has influenced human activity? So basically, what is something that we do as a result of what we are kind of talking about in this cluster? They've talked a lot about kind of this cycle of forest fires, trees, how trees are being used to kind of add and subtract carbon dioxide. We talked here about forest again. And then here they have some ocean atmosphere exchange here. So it says, 1, humans have increased the replanting of trees in areas burned by wildfires in order to decrease the amount of local atmospheric carbon dioxide. So that sounds like a logical thing that we could do. 2 says humans have increased the burning of fossil fuels in order to decrease the amount of carbon dioxide in the atmosphere. Well, increasing the burning of fossil fuels does not decrease, definitely. So 2 definitely can't be correct. 3 says humans have moved to cooler climate regions to adjust to a warming climate. I don't think that we see that on a large scale currently. Most of us do not move north to kind of adjust to climate. So 3 is not so much a good answer. And then 4 says humans have decreased the number of dead trees in the forest by using them as fuel. That would not reduce carbon dioxide, because they told us here that when we have wildfire events, which is essentially burning trees, even if they are dead or alive, it contributes to the carbon cycle by releasing a lot of carbon dioxide into the atmosphere, right? So that would not be a logical choice either. So our best answer was number 1. All All right, question 14. So we're still on the same cluster. We're just adding some more information again. So it says in Earth's past, the carbon cycle has changed due to changes in climate that resulted from several different factors. Changes in the sun's energy, the amount of marine organisms that remove carbon dioxide from the atmosphere, and uplift of major mountain chains have all contributed to variations in CO2. Ice core data provides a record of atmospheric carbon dioxide measured from air trapped in the ice in parts per million, and of Antarctic surface temperature changes over the last 800,000 years, as shown in the graphs below. So we have a carbon dioxide graph here, and it's showing us that we kind of have this like cyclic pattern, right? So we have these increases and decreases, and we notice that they don't necessarily look proportional or consistent. They are kind of varying, but we do see that pattern generally of up and down, up and down. And then we have Antarctic temperature, so how our temperature correlates with carbon dioxide amounts. And we can see that the trend looks generally the same, right? So we can see a pretty consistent pattern in terms of matching with the pattern above. So I would draw the conclusion that there's probably some kind of connection between these two variables, carbon dioxide and Antarctic temperature. So 14 says, which claim correctly summarizes the data in the graph that a change to one Earth system caused a change to another Earth system? Okay, so in this case, they're talking about a change in the atmosphere with carbon dioxide causing a change to our temperature. In our first one, so we're basically just checking with our data, like which ones match up with what we're seeing. So one says increasing atmospheric CO2 levels caused the Arctic surface temperature to decrease over the same period. So we need to find a spot where CO2 is increasing. So I'm going to see right here. So there's CO2 increasing, and we want to look at our temperature change that also increased, headed towards the more positive side. So this is not true because we have increasing and decreasing. They are not indirect. It appears to be a direct relationship. 2 says variations in atmospheric CO2 levels did not affect the surface temperature in Antarctica over the last 800,000 years. So I would say that's definitely not true because our Arctic temperature is changing. So if it was going to not affect it, it should be a straight line all the way across showing that there's been no temperature change. So that is not true. 3 says decreasing atmospheric CO2 levels cause Antarctic surface temperatures to also decrease over the same time period. So I'm going to find a decreasing CO2 level. So I see a fall right here. So it decreases. And I also see a decrease here in terms of temperature. I'm going to check here as well. So I see a general decrease in temperature. I see a general decrease in carbon dioxide. So this is essentially describing a direct relationship where they both do the same thing, and that seems to be true. So I'm going to circle number 3. Let's just check number 4. So atmospheric CO2 levels stayed the same. So 4 says CO2 stayed the same. Again, we would expect a straight line. That's not what we see, so that is also not true. Okay, 15 was a little bit tricky. So it says using the rate of regional climate change in Antarctica for the last 40,000 years, make an evidence-based forecast of how much Antarctic temperatures are predicted to change in the next 40,000 years. So we have to figure out a rate of change. So I'm going to remind you that our rate of change formula involves a change in value divided by a period of time. Okay, so the period of time they gave us, so they told us it was the rate of change for the last 40,000 years. So our T is going to be 40,000 years. And our change in value, we need to figure out how much the temperature changed over that time period. So 40,000, our temperature went from about 0 maybe to about 3. So it went 3 degrees Celsius for a change in value. Change in value. So now if we plug that in, we get 3 degrees Celsius divided by 40,000 years. And if we do that math, we get 3 divided by 40,000 gives us this. And we're going to multiply that by the number of years. So they're telling us for the next 40,000 years. So we're going to multiply that by 40,000 and we get a value of 3 degrees Celsius per year. Okay, so my answer for the first part is 3, and then I need to give an associated impact. So if my temperature was going to rise, I need to talk about something that would happen as a result. So I think that when we're talking about climate change, we talk a lot about like the ice caps say. And so if my temperature increases, one of the changes could be that more glaciers are melting, right? I could talk about sea level rise. So I could say as more glaciers melt, sea level will rise. I could talk about that if more glaciers melt, I might have a decrease in albedo, right? I'm going to absorb more energy because I have less white ice to reflect. Okay, so those are a couple different options that you could say for your associated impact. The big thing here was there was a variation in numbers they accepted. So some people, some ways, if you figured it out, you could have got a negative, and so your change had to reflect your impact. So if you had a negative temperature, you had to talk about what would happen if my temperature decreased versus increased.